After seeing two examples that are not valid, let's study one that is Peterson's algorithm, the check order and competition approach. In this case, we have one shared turn variable and two flag variables, one for each thread. The variable turn is set to A and both flags are set to false. In the entry section, thread A sets its flag to true, sets turn to B, and then waits until turn value is B and B's flag is true. Once A exits the critical section, it sets its flag to false. Let's see why this approach is valid, and let's start with mutual exclusion. We consider the same setup we considered before, and we check if A can enter its critical section while B is in its critical section. What we can say is that before entering its critical section, A needs to exit the while loop. This can happen in two cases, if flag B is false or if turn is set to A. Let's look at the first case. Let's say flag B is false. For B to enter its critical section, it needs to set flag B to true, first instruction of the entry section. Since we are considering the case in which A sees flag B set to false, it means in this case B would set flag B to true after A sees flag B being false. We use an arrow connecting event X to event Y to denote that X happened before Y. After setting its flag to true, B sets turn to ID A. Then B will enter the while loop. Will be exited, not until it sees flag A being false, but that will only happen after A exits its critical section, which means we cannot find a counterexample in this case. We are left with the second case. Let's say A sees the turn value is ID A. Let's resume our previous example. A sets flag A to true, then A sets turn to ID B, and finally A sees turn is equal to ID A and thus exits the while loop. Notice in this case, the value of turn was set to B by A in the second instruction of the entry section, but then B must have set it to A for A to read its ID during the execution of the third instruction of the entry set. After setting turn to EDA, B enters its while loop. Can it exit it and enter its critical section before A? No, because turn is set to EDA and flag A will remain true until A exits its critical section. So also in this case, we cannot find a counterexample. As for previous algorithms, you can switch A and B and show B cannot enter its critical section while A is running its own. Now that we know mutual exclusion is guaranteed, let's check progress. Can it happen that one thread wants to enter its critical section, but it has to wait for unbounded time while the other thread is not in its critical section? Can A want to enter its critical section and be waiting for B, even though B is not in its critical section? It is easy to show this is not possible. If A is waiting, then B can enter its critical section because flag B is true and turn value is ID B. But if B is in its remainder section, then flag B is false, which means A can enter its section. Similarly, if B is waiting, then A can enter its critical section because flag A is true and turn value is ID A. Or B can enter its own because A set flag A to false before entering its remainder section. We are now left with fairness. In this case, we are going to look into bounded waiting. Is it possible for one thread, let's say B, to wait to enter its critical section while A manages to enter its critical section an unbounded number of times? Let's try to find an example of this happening. In this case, A is running its critical section and B is waiting. What we are trying to find is an execution in which A enters again its critical section while B still waits. If this can happen once, then it can happen an unbounded number of times. After exiting its critical section, A sets flag A to false. A runs its reminder section and then starts the loop again by setting flag A to true. Then A sets turn to EDB and enters the while loop. If B is waiting in its loop, then flag B is true. The value of turn is EDB because A just set it. Then we can conclude A cannot exit the loop until B is done with its critical section. Hence, this cannot happen. As before, swap A with B, and the same reasoning applies. So after all this, we can conclude that Peterson's algorithm is valid. Before moving to the next part of the lecture, please have a look at these links about counterexamples and proofs by way of contradiction if you are not familiar with these concepts.